So this time I'll be talking about using and evaluating sentence representations. So this class is a little bit different from the others. It's kind of a survey class where I'm going to talk about a bunch of different things. I have worked on some of these areas before, but very few is my specialty. So if it is your specialty, as always, feel free to make comments or about interesting things that I might be missing. So first, sentence representations. We talked a lot about different ways of turning like a sentence into a vector or something like that, including CNNs and RNNs and stuff. But just to kind of summarize, there's basically two ways that we can express a sentence or represent a sentence. And one is by turning that sentence into a single vector. So we take this sentence and convert it into a single fixed length vector, regardless of the length of the sentence, etc. Or we can do something like convert it into a sequence of vectors. So if we have 4 words in the sentence, maybe we'll convert it into 4 vectors, or we might convert it into even more vectors. So there's a bunch of different ways to do this. So when we get to this point, there's kind of an obligatory quote that I have to post here. This is a famous quote by Ray Mooney, who's a semantics researcher. And right when neural network models were coming out, he gave a presentation at the representation learning for NLP workshop. And I was lucky enough to be there at the time. And basically the quote is, you can't cram the meaning of a whole beeping sentence into a single beeping vector. And basically what he was trying to say here was, these methods for learning sentence representations and then assuming they capture all of the semantics for a sentence are ridiculous and don't make much sense. And I think now there's some evidence that he was wrong, but there's a lot more evidence that he was right. So if he was wrong, the first method will be sufficient. If he was right, then we need something like the second method to generate sequences of vectors. And as I'm talking about all the sentence representations, I will discuss which one this is talking about here. So there's a lot of different ways to use or evaluate sentence representations. These are not all of them, but these are the ones that kind of use sentence representations as a more or less an end product and then do something very straightforward with them, as opposed to something like machine translation or dialogue response generation, which I'll talk about later, where you actually have a lot of downstream tasks that come after the sentence representation. But the ones I'm going to talk about this time are sequence classification, paraphrase identification, semantic similarity, entailment, and retrieval. So the goal for today, as I said at the very beginning, this is kind of a survey where I'm going to talk about a broad variety of things. And I'm going to introduce the various tasks. I'm also going to introduce their evaluation metrics, so how we normally evaluate them. I'm also going to introduce data sets, and I'm going to introduce about how people went about creating these data sets. And I think this is very useful if you want to do something new yourself and want to create a kind of standard data set that other people will use. And this in itself is a very good contribution. It's a contribution that can be very useful for lots of researchers. It's a contribution you can become famous for if that's your thing. So I think that's an important thing to talk about too. And finally, I'll introduce methods. Of course, there's hundreds and hundreds of methods, and I can't introduce all of them. So I'll just talk about a few examples that are either interesting or examples that kind of are achieving state-of-the-art results on these tasks here. So you can kind of reference them if you want. So any questions so far? No? Okay. So the first one, I've actually already talked about this, perhaps far too much, so I'm not going to talk about it in detail, but basically sentence classification is classifying a sentence according to various traits. The example I have given is sentiment analysis, where we turn these into very bad or very good. We can also do subjectivity, objectivity. We can do topic of the sentence, etc. So the task itself, basically take in a sentence, output a label. So most of the methods that we use for these are very similar. So the overall model basically, when we're doing it within a neural network framework, we look up something for each of the words in the sentence. We throw it into some complicated function to extract combination features. I've talked about a bunch of models. It's very, very common to use some variety of convolutional neural network now to do this. Then we use this to calculate scores and use that to calculate probabilities. So basically, all of the talk that I've done up until now has talked about these models. There's a bunch of different tasks that you can do this on. Many of the tasks were cited in the reading material that I talked about on skip thought vectors, or the reading material for this class on skip thought vectors. There are also a bunch of other tasks. But one common one that a lot of people use is this Stanford sentiment tree bank. The reason why I cited this is it's a little bit more interesting than the other ones, where you just have a sentence and a label. This one's kind of interesting because they actually collected all annotations for each of the constituents in this data here. So you can see that not only for the very top label, which is sentiment for the whole sentence, but you also have labels for the other ones. So you can see stuff like what empire lacks in depth. And you can see this part is negative because it's saying it lacks in depth, which is a bad thing about a movie. It makes up for in heart. And you can see that because there's this kind of qualifying statement, the overall thing comes out as positive. So this is a very interesting way of making data that's a little bit beyond your normal sentence classification thing. It also happens to be a standard data set just for sentence classification in general, so it's still worth mentioning in its own right. I'm not going to cover models because everything I've talked about up until now has been CNN models, RNN models, and all of these are used for these tasks. I guess CNN models, particular varieties of CNN models are quite common here. So the next task that I'm going to talk about is paraphrase identification, and this one I'm going to talk about a little bit more. So basically, the idea of this is we want to identify whether A and B mean the same thing. So A and B meaning the same thing, this is kind of actually a difficult concept. So if you look at these two things, these are from a paraphrase database. If you look at these, do you think these mean the same thing? Yeah, more or less. I'd say, so the answer with regards to this paraphrase database, which I'm going to talk about in a little bit, is yes, they do. You can see, though, it does have a little bit more information. Mr. Wheel's longtime confidant, which was not included in the first one. So it's not exactly the same information, but it's close enough that they judged this as correct. So they actually discussed this. This is from the Dolan and Brockett paper on the Microsoft Paraphrase corpus. And they discussed this in detail there. Okay. So now I'll talk about this a little bit. And this is kind of an interesting example of how they created data. So one way they did this was basically they crawled this large news corpus from all the news that Microsoft had on the web at that time, something like 1 million articles. They identified sentences that were similar automatically using heuristics or a classifier. So they basically trained an SVM-based classifier to extract data. And then they also had some heuristics about word overlap and stuff like that. Then they had raters go in and determine whether they were actually, in fact, similar. 67% of them were. So the 67% are positive examples. 33% are negative examples. And then the corpus that they extracted is high quality, but it's small. It's 5,800 sentences. So from their 1 million articles, they extracted these sentences, and they ended up with 5,800. Actually, there's one additional restriction that I forgot to put on here, which is that they had to identify the copyright holder and get permission from them or something like that. So that was an additional restriction that reduced the amount by quite a bit. But anyway, the reason why I'm talking about this also is because I do want people to think about the data that they got, how the data was created. And that kind of puts your models in context as well. So this is in contrast to other corpora. So there are other interesting corpora based on translation or image captioning that you can find. I didn't actually list all of them here, but you can find them online. And one other way to create paraphrase data is to take a sentence in one language and then ask people to translate it into another language. And then you'll get these translational paraphrases. And this is a very good way of extracting, for example, paraphrasing rules automatically. Another one is image captioning. So you take an image and you ask 10 people to describe it. It's a very similar idea as the translation. But that's another way to get data. But these ones are naturally occurring in news, for example, and they can extract things that way. So there's a bunch of different models for paraphrase detection. So this is kind of where the various varieties of sentence representation come in. So one way to do so is to calculate a vector representation. So you get, then you feed the representation into a classifier, and it decides yes or no. So this is you can cram the meaning of an entire sentence into a single vector approach. And there's a variety of models that try to do this. And perhaps one of the more interesting varieties of models, or one of the more widely used varieties of models in this is skip thought vectors. Have people heard of these? Yeah, to some extent. Okay, so this is basically the sentence level version of the word2vec, except that it's not really the sentence level version of word2vec. It's neither the skipgram model nor the SIBO model. What it is like is it's kind of like a positional version of the SIBO model, where you take in a sentence, you read it in, and then you try to predict the sentence before with one kind of decoder, and then you try to predict the sentence after with another decoder. And this is a variety of the encoder-decoder architecture that I'll talk about before. But the interesting thing about this is entirely unsupervised training. So all you need to do is you need to have a document where you know the order of the sentences in the document, and then you can calculate based on this. And that gives you relatively good vectors there. And then you can use the resulting vector as a sentence representation, and then just put it into a classifier and try to decide whether it is a paraphrase or not. And the way they did this, so this is a pretty good way of doing this, I think. What they did was they took the absolute value of the difference of the two. So if you have exactly the same sentence, of course, the absolute value of the difference will be 0. Then they also took the component-wise multiplication, and then they just used a logistic regression over this. So the idea behind this here is basically that certain elements, if they're very similar, will be very indicative that things are a paraphrase, and other elements, if they're not very similar, even if they're not very similar, will not be very indicative. Are there any questions about this? Yeah.
Would it be wiser to normalize the second term?
So would it be wiser to normalize the second term? So one thing I should mention is that these are component-wise, both of these. So one is the component-wise difference. One is the component-wise multiplication. So then they're just feeding this into a regressor. So there's no... you probably don't need to normalize, I guess.
Yeah, I wasn't sure.
Okay, yeah.
Because I was thinking that more like a dot product and then.
Yeah, you could also do the dot product or the cosine similarity, which is the normalized version of the dot product. But yeah. Okay, so I will move on to the next one. So this is you cannot cram the meaning of an entire sentence into a single vector method. So these methods actually calculate a multiple vector representation and combine them together to make a decision. So sorry, actually my example here is not a very good example because these are exactly the same sentence. So it's kind of a trivial paraphrase detection problem here. But imagine that those were different sentences, and then you would calculate the vector representations and need to decide yes or no. And I actually talked about this last time, but basically the common way to do this, there's quite a few different methods that were proposed to do this, and they all kind of have the idea of having one kind of a sentence-based representation and then doing some sort of pooling to get a representation in the middle. Usually it's kind of a dynamic pooling operation where you take things of two different lengths and turn them into a fixed length representation. This particular one had multiple levels of like convolution and other things. There's also earlier work by Richard Socher et al. And others that used a single level using a tree structured method. So, but this is another kind of common way of doing paraphrase detection. In terms of which one works better, this one tends to work better. The reason why it tends to work better is, let's say you have two very, very similar sentences. What you can do is you can kind of see that because the similar sentences tend to have similar structure, you can see that the area down the diagonal basically consists of very, very similar values. And if you see a pattern like this, basically you can almost look at the image of the similarity vectors between these. And it becomes an image recognition problem where a human could look at the thing and tell whether it's a paraphrase or not. So of course a machine, which has now exceeded human performance in image recognition, maybe, or maybe not, can do this as well. Then, as I promised, I will also talk about kind of state-of-the-art methods. So very, very interestingly, actually the state-of-the-art method for this paraphrasing corpus, which has been around for 2005, is not a neural network-based method. It's a matrix decomposition-based method. So what they did was they basically they created a big word context matrix, and they weighted each of the word context weights based on their how discriminative they were for the paraphrasing task. So this thing on the upper right is basically a matrix, a measure of how discriminative the words are. So words like fear or nor or but or not are relatively discriminative. And then they did this matrix decomposition to lower the dimensionality and then made predictions based on that. Importantly, they also added features regarding surface match. So that's to take advantage of something like this, but these were not neural network-based features. They were just text match-based features like the BLUE score or something like that. For those of you in this neural networks for NLP class, you can take this as a challenge. Since 2013, nobody has been able to come along with a neural network and beat this approach. So if you're interested in paraphrase identification, now's your chance to to come up with a method to do this. Go ahead.
Is this on the 5,000 sentences data set?
So no, this one used additional data, but so did a lot of the other ones, like the skip thought vectors paper, which is a neural network-based method, also used a big book corpus. So I think generally For unsupervised training, it's assumed that it's okay if you do unsupervised training on some other data. So, yeah. Okay. So, are there any other questions about paraphrasing? That's about it.
What was
Yeah.
surface matching the previous slide?
Oh, okay. So it was just the number of unigrams set match, the number of bigrams set match, the blue score between the paraphrase and the non-paraphrase, and other things like that. So I think this method isn't competitive without these surface features, but their surface features are very powerful. And before this method, I think the best method was one that just took a bunch of evaluation metrics that were designed for evaluating machine translation, combined them all together, then trained a classifier that used those methods. So this is kind of an expansion on that without using all of them, but just using blue score. Okay, so I'll move on to the next one. So this is semantic similarity. So semantic similarity, basically the idea is, do two sentences mean something similar? So I talked about this in the word embeddings part as well. But basically, this is where you take a subjective evaluation about two sentences being similar or not. So a man is jumping into an empty pool, and there is no biker jumping in the air. These are judged as very not similar, or not very similar. And a person in a black jacket is doing tricks on a motorbike. A man in a black jacket is doing tricks on a motorbike. Those are judged to be very, very similar. So what we would like to do is, so as a task, this is like paraphrase identification, but with shades of gray. So basically, we are trying to, regress to this relatedness score instead of making a yes/no decision. And an example of this is the SICK data set. Have people heard of this before at all? Some people? Not too many. But basically, this data set had actually, to be honest, I spent a lot of time preparing for this class because I have not actually worked on these myself. And actually, the data preparation details are something, I knew this data set, but I didn't know the details. And it's actually quite important when you look at papers that evaluate on these things. But this had a very unique procedure to create sentences. So they started with short Flickr video description sentences. So these are sentences, Flickr or video description sentences. So these are sentences that describe a video or sentences that describe a picture. So this is a very popular way of getting short descriptive sentences now. Then they normalize the sentences. So they do basically 11 types of transformations that try to change the sentence into something similar, but that still means the same thing. So they do things like switch the passive and active. They do things like replacing with synonyms. Then they also create opposites. They insert negation. They invert determiners. So a man becomes no man. Then replace words with antonyms. So man becomes woman. I don't know if that's an antonym or not, but something different. Then they also scramble words in a way that doesn't preserve the meaning. So that would be a man is jumping on a bike versus a bike is jumping on a man, or the man that jumped on the bike flew, or something like that. And then finally, they ask humans to measure the semantic relatedness on a 1 to 5 Likert scale of completely unrelated versus very completely unrelated to very related. So this is a commonly used data set. It's kind of interesting because there's lots of lexical overlap, but you have to look at the structure and opposites, et cetera, kind of difficult things to find the differences between them. And then for the evaluation procedure, it's simple. You input 2 sentences into the model and calculate the score. Then you measure the correlation of the machine score with the human score. So then you can use Pearson's or whatever your favorite correlation measure is. Here's a model example. I looked this up. I believe this has gotten the best results on the task that I've seen. I might be missing some of the more recent stuff. But this is a Siamese LSTM architecture. So basically, what a Siamese architecture means in the framework of neural networks is you use the same thing on the input and output side. So we have an LSTM that's used to process both the input and the output. Then we have some sort of similarity measure, which is then calibrated between 0 and 1. And then this is used to basically regress on the similarity measure. Here they used a kind of interesting way of measuring similarity, which is basically the L1 norm of the distance between the embeddings, which is then exponentiated. So if the distance is 0, then you get 1, and if the distance is higher, you get 0, basically. And they trained this. So this is incredibly simple. It's way simpler than all the other models here, yet they get very good results. My conclusion about this is that probably they engineered their model very well. I'm not sure whether the core contribution is what made this work very well. I'd be very interested in asking the authors, and I may do so after this. But they have lots of kind of engineering tricks that seem to make this that should help, like pre-training word embedding, pre-trained word embeddings, etc. And this, at the moment, seems to be best reported or very good accuracies on this task here. So I guess the conclusion here is that nifty, cool architectures are important, but engineering, if you really want to get the best results, are important. So that's another takeaway from this, I guess. Any questions? Yeah.
So do these sentence embedding approaches differentiate between sentences that are syntactically valid but semantically correct?
So the question is, do they discriminate between ones that are syntactically valid but
What are semantically incoherent, say? So do they get clustered away from things that are semantically incoherent?
So that is not the task that I'm talking about here. That's an interesting question. I'm not sure if I can think of any particular task that tackles that other than language modeling. So language modeling, you kind of get that for free, because if it can't discriminate between semantically incorrect and semantically, likely sentences, it will lose perplexity. But I don't know. Does anyone know of a data set that tests that or something? Yeah, I don't know of any myself. So
So the reason I was asking was
Yeah.
data set seems to have been created by a lot of compositions where you replace what you insert certain modifiers.
yeah.
But these, how did they ensure that the resulting sentence is still valid?
Oh, so the question was, how do they determine whether the resulting sentence was still valid? The answer is that they did all of these steps manually. So this is all entirely manual. I've seen a couple papers recently, I don't have the references right now, where they actually do try to do things like swap in words. Like for machine translation, for example, augment your data by swapping in words into particular positions. That might be correct, or that might be incorrect. Those ones you need to worry about more, but in this case, it was all manual. So. Okay. Any other questions? If not, I will move on to another one, textual entailment. So there's this textual entailment task. So the textual entailment task is basically you want to determine whether it is the case. If A is true, then B is true. So this is very useful for things like question answering It can be it can be kind of an element of a question answering system where basically you're given a text and you want to decide whether a question, a multiple choice question, is correct or not. So if you wanted to build a system that took all your quizzes in this class for you, one way you could do that is you could basically have a thing that read the entire text that I asked you to read, and then then answer A, B, C, or D on the quiz. And that would be a textual entailment question where it would be able to say no to all of the wrong answers and yes to the correct answer. And I know your second question is, can I use that system to answer all my quizzes for me? And the answer is yes, if you can make one. Feel free to use it on the quiz. Just tell me first. So anyway, this is in contrast to paraphrasing. So paraphrasing is often considered mutual entailment, where both of the sentences have to entail each other. This is a little bit too strong of a requirement, though. So like the Microsoft Paraphrase corpus, they explicitly say that this is too strong. We can't find any paraphrases that actually satisfy this requirement, so we need to loosen it a little bit. The opposite of entailment is contradiction. So if A is true, then B is not true. The woman bought a sandwich for lunch, so the woman did not buy a sandwich. At first glance, it might seem that these are just, these cover all the sentences, but if you know your logic well enough, which I assume most people in this room do, you'll realize that there's also a large number of sentences that don't do either of these. So they're not mutually exclusive, nor are they entailing. So the woman bought a sandwich for lunch. The woman bought a sandwich for dinner. It might be unlikely, but it's quite possible that somebody would eat sandwiches 2 times a day. So this is neutral. Okay. So a data example for this. This is a somewhat, I guess a somewhat well-known example. This is the Stanford Natural Language Inference dataset. This is also created from Flickr captions. So this is what everybody likes to do nowadays because you get these short, relatively easy to process sentences that are still interesting. Then they crowdsourced the creation of one entailed, neutral, and contradicted caption for each caption. So they basically had easy to understand wording that explained what entailment was, what contradiction was, and what neutral was. Then they verified the captions with 5 human judgments, and 89% of the verification agreed between the annotator and the gold label here. So it's a relatively high quality, and most importantly, it's 500,000 sentences. So if you have 500,000 sentences, then you can start to train a model that actually captures all of the interesting stuff here. Also, relatively recently, there was an expansion to multiple genres, multi-NLI, which was also released. So this is kind of the successor to the Stanford NLI, and it's much more interesting because it covers a bunch of different spoken and written genres. Okay. So this is a paper I found on this recently. This is a more kind of, it's a model that was basically tailored to this task, but you could also probably use it for other tasks. But basically what it does is it has this kind of attention-based model. I'll talk more about attention in 2 classes. But they basically take in each vector in one of the sentences and combine it with all the vectors in the other sentence to create a representation for that particular word. And then they run a by LSTM over these, extract the last states of this LSTM, and then put all of these into a softmax. So this is trying significantly harder than some of the other models that I talked about before. But this seems to work pretty well. And then there are others. But an ensemble of these models currently has the best results on or some of the best results on the website here. And you can also, one of the nice things about this is this website has a list of all the models along with their accuracy. So you can go in and look and see the various architectures that people have used for this problem. So an interesting paper that just came out at EMNLP This is in contrast to the skip thought vector paper. So if you remember the skip thought vector paper, what it was doing basically was it was predicting contexts. So it was taking in a sentence and predicting the sentences that appeared around it in a discourse. So these can be considered unsupervised training. So the good thing about unsupervised training is you can get millions and millions of sentences, right? You can download a corpus of all the books ever written, all the Wikipedia documents, etc. And you can get basically in unlimited, not unlimited, but very large amount of training data, especially for a popular language like English. And then the simple question about this that this paper posed is, can supervised training for tasks such as inference do a better job at learning generalizable embeddings? And there's two hypotheses that we can make here. So basically, the inference task is more difficult. It's nuanced and it requires capturing more difficult linguistic phenomena. So this would kind of lead us to believe yes. But the data is much smaller, so this might also lead us to believe no. And basically what this paper showed is that, yes, in general, by training on specifically the Stanford natural language inference or multi-genre natural language inference data set, you can get embeddings that work well on a wide variety of tasks. And I think it was pretty conclusive in that it worked better for like 10 tasks and worked worse for 2 tasks or something like that. Of course, you could do both if you wanted to. So they're not mutually exclusive, but I thought this was interesting, that we do need to think about the task that we're using. So are there any questions? So there was actually kind of an interesting demo of this that just went online. If you want to play with this, so let me see if I can pull this up. If I can pull this up now. So there's this demo of from the Allen Institute for AI, and they have textual entailment models, and you can put in 2 sentences where the premise is a black dog chased a cat through the doorway, and the cat is black, I think was the example that they had. And you can run this, and it says this is entailed, which is not correct. Then you can also say black is red, or the dog is black, the black is dog, and this will also be entailed. So I think part of the problem is the training data. Part of the problem is I think they were only using the Stanford natural language inference, and if they use a multi-genre one, it would be better. But if people report high numbers for this natural language inference task, you can still be assured that there's still lots of work to do here. So if you search for this on Twitter, you can find lots of other nice examples of people playing with this and pointing out all the things that this is not able to handle yet. Okay. So I will go back to the slides. Are there any questions about entailment-related stuff? No. Okay. So now I will go on to retrieval. So I'm going to spend a little bit more time on this than the other ones, just because it's more involved and it has more moving parts. But the basic idea is that we have something in a sentence. a big database, and given an input sentence, we find we want to find something that matches that in the database. So, for example, we might have text-to-text retrieval. One example of text-to-text retrieval would be you put in a search query and it gives you a document. So then your input is the search query, the output is the document. Another example would be if anybody uses Gmail on your phone, you put in your email and it retrieves a good response for your email, like if it says, I would like to schedule a meeting with you, how about Thursday? It will say, sure, Thursday is great, or I'm sorry, I'm busy on Wednesday, or something like that. So sometimes it works, sometimes it doesn't. Another very common one is text-to-image retrieval. So you take in text describing an image and you want to retrieve an image. And this is good if you want to do like image search or something. And you can do this for anything to anything. So anytime when you have a database of results you want to search over, you can create a retrieval model. So the basic idea is we have this database where we want to do retrieval over it in some way. So the first thing we do is we encode all of the things in the database as vectors, and then we save these somewhere. Then we take our input. We also encode this as a vector. And then we just find the closest vector, the vector with the minimal distance over all of these. So it's a pretty well-formed procedure. It's easy to do. We know how to encode sentences as vectors. Of course, you still have the problem of whether you can encode a full sentence in a single vector, but assuming that we can do something pretty close to that. So then we want to train this model, of course, because we have neural networks with lots of parameters that we would like to train. And so given this, let's say we have our current model where we can encode all of these as vectors, and we can encode our query as a vector. From this, we can calculate some score. We can have a score where we input both of these and calculate a score. And let's say the wrong example, the one on the top, gets a higher score than the example on the bottom. So basically what we do here is we assume that this is bad. And then we penalize it in some way. Another very, very common thing to do in these models is to introduce a margin. So the margin is basically saying not only is it's not good enough to be better than the other bad examples. We have to be better by a certain margin. So we have to be better by at least 1 point. And in this case, our good example is only better by 0.2. So we want to penalize this. Another problem is that we might have a very, very big database. So the database could be all the web pages on the web, for example, if we want to do web search. Or it could be, all of the email responses that anybody has ever done to an email. And if that's the case, we can't reasonably do training over all of these examples. So we take a trick from basically the Word2Vec or language modeling book, where we only randomly sample a few of these as negative examples. And then we use these use only the randomly sampled negative examples and then do training over these. So to put this in equations, we can calculate a loss function that looks a lot like this. So we have our true input x, our true output y, and then we have s, which is a bunch of negative samples. We calculate a hinge loss where it's basically the maximum of 0, and then 1 plus the score of the bad example minus the score of the good example. So if the score of the good example is more than 1 better than all the bad examples, this will be 0. Otherwise we'll incur a loss here. So yeah, that's the correct input, correct output, negative samples, incorrect score plus 1 incorrect score. Is this clear to everyone? Yeah. Is the training data what? Yeah, so we assume that we have some sort of training data. So we have, like the paper that I cited on web search, basically they assumed that if you clicked through, then it was a good example. If you didn't click through, it was a bad example. For image caption generation or email response generation, you can get an image and its true caption, and then all the other ones are negative, basically. In the example I have here, in the example I have here, I actually have a translation retrieval example where you have an input is a Japanese sentence, output is an English sentence, and we know which are translations. So then, how do we measure the accuracy of these? We have recall at x, where basically is the correct answer in the top x choices. So recall at 1 is did you get the number 1? The correct one is your number 1. Recall at 10 is did you get the correct one in your top 10? And recall at 10 will always be higher than recall at 1. You can also do mean average precision, which is area under the precision recall curve. This is nice because you don't have to set an x and it gives you a single number. I think both of these are used pretty widely. So I said let's try it out on text to text, and I'll do that in a second. But actually, while I explain the training code, this is included in the training code, so I should explain this first. One way to do this efficiently is to basically use mini-batch training. So if you remember, mini-batch training is where we take multiple sentences and then process them all at the same time. So the way we do this in Retrieval is we sample a mini-batch. We calculate representations for all of the inputs and outputs, and then we use all of the other elements in the mini-batch as negative samples. So basically the idea would be this S here, these are our negative samples. These are all the other sentences in the mini-batch when we calculate this hinge loss. So we sample 16 sentences and then step through one by one. And this S would be 15 sentences large. It would be all the other ones in the mini-batch that we sampled. And this is good because then we can process all of the sentences only once instead of having it linearly increase. Okay, so this one is the one implementation example that I have here. So I will open it up. And first, a very brief look at the training data. The training data looks like this. It's just Japanese sentences and English sentences. These are relatively short sentences. And the idea is we have a training set where we want to be able to learn representations of Japanese or English. And then we have a development set where we would like to be able to retrieve those appropriately. And so here is the code. So here we have our training files, our development files, and then we have our kind of boilerplate stuff. This boilerplate, basically what it will do is it will read in pairs of source and target sentences. So once we're done reading, we'll have this big corpus of tuples where the input tuple is the source sentence, the output tuple is the target sentence. Then we have all our normal stuff. We have the embedding size, where the embedding is the size of the vector we look up for a word. The hidden size is the size of the hidden state in the LSTM, in this case we're using. Then we have our batch size, which is the size of the batch that we're using to do calculation. This will also be, 1 minus this will be the number of negative samples that we use in calculating our loss function. We then, so I am not using a Siamese architecture in this case. So the Siamese architecture, if you remember, is the one where we share the parameters for the input and output. In this case, we're looking up Japanese on one side and English on the other side, so I decided not to do this. If we were doing something like dialogue response generation, where we want to take an input in English and look up and retrieve an output in English, then maybe it would be better to share the parameters between all of these. So, but in this case, I have separate parameters for the source and the target. Then in our training loop, we basically loop through the, let's see. We loop through the training data. We find a batch of data. and we send the batch of data to the calculate loss function. And what the calculate loss function looks like is like this. We renew the computation graph. Then for each of the sentences in the batch, we basically transduce that sentence. So that means step over all of the elements in that sentence with our bidirectional LSTM and calculate the representations for every word of that. Then we take the representation for the last word here. Then we do the same thing for the target. So once we've done this, we have a list of sentence representations for the source and the target as basically DINET expressions here. Then what we do, the next thing we do is we concatenate these into a matrix. So for the source representations, we create a matrix of the source. So this matrix, I'll write the dimensions here. This matrix is the embedding size by the batch size. We have this for the source and the target. Then what we can do, because we're taking the dot product, you can calculate the dot product using a matrix multiplication. So that is that's this thing here. So what we're doing is we're transposing the source vector, and as a result, if we transpose this, this becomes a 16 by 128 vector, and the multiplication of this becomes a 16 by 16 vector, or a 16 by 16 matrix. Sorry. And this is the matrix of the scores between each of the examples. And then we can take the hinge loss over this. This hinge loss function basically will allow you to take the hinge loss over a particular dimension. And in this case, what we're doing is we're taking the hinge loss where the correct answer is down the diagonal. And the reason why we can do this is because basically the diagonal is the ones that match, and the non-diagonal ones are the ones that don't match. So this is an efficient way to calculate these representations. I think you might have gotten it. If you didn't get it, then then you can take another look at the code, and then I'm happy to answer questions later. So then the next thing we need to do is we need to do actual prediction or actual retrieval. And so the way we do retrieval is we do this by indexing the corpus. So the way we index the corpus, or we create representations for every sentence in the corpus. And the way we do this is basically by stepping through all of the sentences in the corpus to calculate these. Just doing this would not be very much fun. So I did 16 sentences at a time, or I did batch size sentences at a time. And the reason why I did this is because if you use DINET's auto batching functionality, if you do 16 at a time, it will become faster than if you do just several at a time. You could just take this out of this inner for loop, and that would make things slower, but it would give you exactly the same result. Then when we want to do retrieval, basically what we do is once we've indexed our entire target corpus, we can stack together all of the vectors into a big matrix. So the way we stack together the vectors is basically we have 128 here, and then maybe 500, because 500 is the size of our development set. So 500 is the size of the corpus over which we're retrieving. And we can use the NumPy stack function to do this. Then we perform retrieval, where we calculate the ranks, of in ascending order or in descending order of score. So the number one will be the one with the highest score. The number two one will be the one with the second highest score. And we can do this with the NumPy dot function. And then we can basically calculate the ranks by using the NumPy argsort function. So we can then do retrieval, and we can calculate the recall at 1 by adding 1 every time we get it correct. We can calculate the recall at 5 by doing it every time the correct one is in the top 5 ranks, and the recall at 10 by doing 1 every time it's in the top 10 ranks. So, so that's kind of the overview of the retrieval thing. And because it might be of interest to see it run, I will let it run and hope it doesn't crash. And as always, because I'm recording a video here, it will take a little bit longer than it did on my previous computer. But actually, that's taking a horrible. This is totally different than when I'm not taking a video. Normally, it's finished 1 epoch by now, and it hasn't even finished 500 sentences. So yeah, it's 10 times slower because I'm taking a video. Let me see. Okay, I was going to do something later where I tried it with the auto batching functionality and checked whether it was faster or not. But I'll do it now because otherwise it won't finish. But were there any questions about the code or anything like that, or about the ideas here? Yeah.
Does it mean that we need to turn all the training data in vector at each step of the training process?
Do more training data at each step? Yeah.
We need to turn all the training case into vector at each step of the training process.
So at each step of the training process, you use a single mini batch, which in this case was 16 examples. It needs to be more than 1. It could be just 2, where you have one positive example and 1 negative example, but it needs to be more than 1, because we're using the other sentences in the mini batch to calculate our negative examples. Is that okay? Okay. Any other questions?
But in the like prediction part, we need to turn every sentence.
In the prediction time, yes, that's a good question. There was a typo in my in my commands here, so I realized it wasn't doing auto batching. So the at retrieval time, in reality, what you would need to do is, if you were doing a web search task, you would need to search over all of the pages in the entire web. When people evaluate these models, they usually evaluate by only doing retrieval over the deb set. So they're actually making their job a little bit easier, because if you make it smaller, then it's easier to retrieve. But usually it's standard practice to basically to evaluate over the deb set only.
But could we apply this kind of model to like document retrieval, because what you mentioned is like they just sentence if it's document which the text may be much longer than sentence.
Okay. So the question is, could you apply it to document retrieval? And the answer is yes, you can. And in fact, the paper that I cited is doing that. They're doing search query to document retrieval. It becomes a very interesting question of how you make your encoder for the documents, right? So you might have to try a lot harder to create a good encoder for documents than you would otherwise. Cool. So this was doing 600 sentences a second when I wasn't recording video, and now it's doing 52. So I'll leave this running while I finish up the rest. But if there are no other questions about this, I will move on to the final part. There's a few improvements that you can do to this. One is bidirectional loss. This is a pretty standard thing to do. And basically, all you do is you calculate the hinge loss in both directions. So what I was doing here was we basically had this matrix, and what we were doing was we were comparing this value to all the other values in the column and trying to make sure that it was higher than all the other values in the column. So the idea behind this is you also do it for all the other values in the row, and you basically get a learning signal in both directions, which is basically free to calculate compared to all of the other things you're doing. It's super cheap to calculate compared to all the other things you're doing, and it trains a little bit better. So this is pretty standard. Yeah. Was there a question? No? Okay. Also, if you're not just evaluating on a dev set of 500 examples, but you actually want to make this work for large data sets, the way you can do this is through approximate nearest neighbor search. So the idea is that you're going to want to get some sort of basically representation, vector representation for this. And you want to find the closest vector representations. And the way, one common way to do this is through locality sensitive hashing. There are other ways. But locality sensitive hashing, basically the idea is that you calculate a loss function, a hash function that takes in this vector representation and calculates a hash for it. And the way you calculate a hash is, if you have a point in space like this, you basically calculate a bunch of vectors. So this might be vector number 1, this might be vector number 2, and this might be vector number 3, or plane number 3. And then you find which side of the plane this point is on. And it's on the good side of plane number 1, the good side of plane number 2, and the bad side of plane number 3. So essentially, you get a hash function of 110, which allows you to pare down all of the other very similar things and only search over a very small subset of the whole database that you were using. So this is one way to do efficient search. In terms of an example of data, there is image retrieval. This is a very widely used one. There's also lots of others. But the input is a text, the output is an image. And for the images, you're already given image features, basically. People have pre-computed image features using a large convolutional neural network trained on an ImageNet. So if you want to do something like this, the image processing is done for you already. There's also 8,000 images. They each have 5 captions that were crowdsourced. So you can find different ways of saying a particular image. Yeah. So that is all that I have for today. If there are any questions, I'm happy to answer. If not, I will you can see that this is trained and it's achieving a recall at 10 of 18% after the first iteration. So the model is learning. I think this goes up to about 40 or 50 or something like that. Recall at 10. This is less interesting than something like dialogue response generation, where you can retrieve responses. And actually, we found generating responses is better if you have good training data, but actually dialogue response generation is a really difficult task. So something like retrieval is a very strong baseline that you can also try in addition to generation if you're thinking about doing something like that. So I guess that's all I have for today. So thank you very much.